But which one has delocalized electrons? Delocalized electrons.
Graphite.
ठीक है, graphite, graphene, and Buckminster fullerene. ठीक है, diamond is the only one. I'm going to just quickly go through all of them. Diamond is sp3 hybridized. All carbon electrons are involved in bonding. All four of them. They're bonded to different atoms, so they're all busy. ठीक है, only when carbon is sp2 hybridized, when it's bonded to three atoms, like in graphite, the fourth electron ends up forming a pi electron cloud. Uh, so this gets kind of delocalized. So we already know about graphite. I'm just going to quickly show you the structure of graphite. Just 1 second. This is graphite. Uh, so this one over here is graphite. You get the one on your screen. Does anyone have any idea what graphene is? Anyone कोई idea? What's graphene? Bhaskar, any idea? Reda, Eba?
Neither, never heard of it.
So I'll just quickly go through that. Graphene is the same as graphite. Graphene is called as a single sheet of graphite is known as graphene. This is what graphene is. So if you are able to isolate a single sheet of, I mean, this diagram is very clear. If this is graphite. Ibrahim, your mic is on. This is graphite. Graphite is when you have layers, sheets of carbon, and all of these carbon atoms are sp. Where's your rough? Just 1 second. I'm just going to show this over here. TK, this is all rough work. This is what the structure of graphite looks like. It's sp2 hybridized. Carbon is bonded to three atoms, all of them. So it's forming hexagonal layers. Each carbon atom is bonded to three atoms, right? So what eventually happens to this type of carbon, it's sp2 hybridized, which means that each carbon atom has this fourth electron, the fourth orbital, which is not doing anything. And remember, we did the structure of benzene. In benzene, we discussed that when you have so many orbitals parallel to each other, they all start overlapping, they all start forming pi bonds. But the pi bonds, they become delocalized because all of them would start overlapping with all of them. So they all start to overlap, and you get this giant pi electron cloud. Okay, so there's this giant delocalized pi electron cloud, and it's completely delocalized. Okay, is this clear? Abba, is this clear?
Sir, I don't get what you're saying, completely delocalized.
Delocalized means that the electrons can now move freely. They're no longer independent. Like localized is, let's look at an ethene molecule, right? Or a propene molecule. This is carbon atom with three bonds. This is carbon with bonded to three atoms, right? So these two carbon atoms have this fourth electron, and this fourth electron can start overlapping and they can form a pi bond. Okay, so Ibrahim, is that clear? I mean, this is a pi
Yes, sir.
electron. But the pi electron cloud in an alkene cannot move anywhere because it's stuck over here. It can't go anywhere. Is that clear as well?
Ji.
So this one is called localized. Like it can't go anywhere, right?
Acha, why can't it go anywhere?
I mean, where would it go? The electrons are stuck over here. Like, where would they overlap? There is no other. All the other electrons are busy. Okay.
Acha, yeah.
Sir, this electron cloud is basically the second bond of carbon, right? The extra one, that's basically the double bond.
The pi,
right?
Pi bond.
Right. So if we talk about any other atom, why are we calling it like delocalized? Because if we take an example of any other atom, for example, chlorine, that's Cl2, it's also having double bonds.
CO2 की बात कर
Oxygen
रहा
is
ना?
having,
तो
if
CO2.
we take an example of oxygen, it's O2. So it's having double bonds. So the double bond is always going to be the delocalized one.
Nee, the double bond is localized. I mean, over here, I gave you the example of propene. I mean, the double bond is not going anywhere, right? The double bond is always over here. But is that clear?
Okay, if we take an example of CO2, right? So
Uh,
carbon is like oxygen has double bonds with carbon. So that's the first one, and the other bond that will be delocalized.
nee,
The other bond of
it
oxygen.
won't be delocalized. Like carbon had these two spare orbitals, right? In CO2, okay, let me discuss CO2. In CO2, carbon was making one sigma bond over here. One of its electron was shared by one oxygen over here. And carbon had two orbitals that were initially not doing anything, right? They were on different axes. So they would end up forming double bonds with oxygen. They would form because oxygen had.
Okay, these are two different atoms. Okay, I get it.
I
Yeah,
said,
get it. I get it.
so just quickly, there would be this other oxygen, and they would form. I said they would also form pi electron clouds. Okay, but over here the pi electron cloud is localized. I mean, it's not going anywhere. It's right over there. In ethene or in any alkene, the pi electron cloud is also localized. Okay, but when you have lots of p orbitals and like each carbon atom is sp2 hybridized in graphite. Okay, every carbon atom is bonded to just three atoms, which means that the fourth electron is available, and the fourth electron is not doing anything. The fourth orbital with its electron, it's just lying around. And what happens when the orbitals in parallel, they start overlapping. They start pulling each other's electrons and the electrons. But since there's uh, so many of these p orbitals present in graphite, that the electrons they kind of all mix up, and you have this giant electron cloud and the electrons can move anywhere they like. Okay, so this electron, if it's overlapping with this carbon atom, it could also move and it could start overlapping with the carbon atom on that side, or it could start overlapping with the between the carbon. So the electrons can sort of move around. They're now completely delocalized. Is this clear? Rida, Hiba, is this clear?
Oh, it's clear.
Sir, does that mean that such structures can be polar at times?
Why can they be polar at times? I mean, everything can be polar at times, and temporary dipole induced dipoles can always be formed.
Hmm, exactly. Right.
See,
Because hydrocarbon chains are usually non-polar, right?
but they have van der Waals forces. Van der Waals forces, which means whenever something is called non-polar, it still has van der Waals forces. Like the
Hmm.
electrons can always get disturbed by anything, by collisions or uh, by any random movement. Like they can hit the wall of the container, or they can just vibrate. And so the electrons, even if the molecule is completely non-polar, there would be temporary
Mhm.
dipoles and induced dipoles. Like the electrons can
Still it one. Exactly.
they can so they're temporary dipoles and induced dipoles. So
Hmm.
unlike permanent dipoles, there won't be any permanent dipoles, but the electrons can sort of go about, move randomly, right?
So kind of one part of the molecule can have a partially positive and the other part can have
Ah,
a partially negative
that's
charge.
why graphite has van der Waals forces. Where is graphite? This
Okay.
one over here. That's why graphite has these weak van der Waals forces. Okay, clear? है?
जी sir.
ठीक है? Is this clear to everyone else as well? The structure of graphite. Abba, Rida, Heba, is this clear?
Yes.
Yes.
Acha, so I was coming to graphene. Graphene is a single sheet of graphite. Okay, if you have a single sheet of graphite, that is graphene. Not a lot of detail is required for this. It's just you just need to know or identify the structure of graphene. It's a single sheet of graphite. Why is this sheet so important? Uh, Previously, graphite, whenever you had graphite, graphite had billions of layers of these graphene sheets. And scientists were not able to actually isolate a graphene sheet. It was impossible to isolate a graphene sheet. Somewhere around 2001 or somewhere in the late 90s, somebody got a Nobel Prize for actually isolating a sheet of graphite, which was called graphene. And this was a big breakthrough because because this thin layer is very strong, and it's flexible. You can make different structures. That's where nanotechnology comes in. The same sheet, it's like you have a big thick book, a copy with many pages. That's graphite, and somebody has been able to pull one page out. Now that copy, that entire copy, if you have a big thick book, you can't really fold it. You can't really make shapes out of it, right? But if you're able to pick one page out of that copy, that page is very flexible, and you can make different structures out of this. This is called a buckminster or a buckyball. This is known as fullerenes. They're spherical structures. Then there are tube-like structures. So these are these tiny nanoparticles that can be created, and these nanoparticles can be very useful, especially uh, for many different things. Actually, gas from gas storage to first thing, do you get the point how what's happening here? Ibrahim, is this clear?
सर ये
Or
बक ये सर्कल जो है ये क्लियर नहीं है कि
नहीं,
how does it make shapes?
what are different you do different treatments on it. Okay, for example, electricity is passed through. uh, a simple example, if you take out a page out of a copy, right? uh,
Mm-hmm.
if it's in a copy and stacked with all the other pages, it remains straight, right? And it's
Exactly.
it's very unflexible. You can't really tear a copy, you can't really bend it or fold it or make it into a circle or a sphere, right?
जी
But if you take out a page, so the page is very unlikely to remain straight, right? It's going to get crumpled.
जी
Okay, so that is exactly what happens to graphene. That
अच्छा
graphene,
अच्छा
but it's not going to
जी
remain. It's not going to remain flat, uh, and it folds up. It makes these random structures, which are known as nanotubes and known as fullerenes. These are fullerenes. These are also called buckyballs or buckminster fullerene. If I give you, and there are many different types of fullerenes. It's like a football. It's exactly the same structure as graphite, but it could have many different sizes. Okay, so you could have you could have a 60 carbon atom structure or a 70 carbon atom structure or a 24 carbon atom structure. So many different types of structures are possible. So these are fullerenes. These are your nanotubes. Okay. Abba, is this clear?
Clear.
I said now one interesting thing happens. Think of think of the copy and the page example. You take out a piece of you take a page and you roll it into a tube-like structure. The page is very I mean, it doesn't have a lot of strength, right? Like the page is very flexible, but as soon as you roll the page into a tube-like structure, it kind of becomes very strong and very rigid. Is that clear, Ibrahim? Basga, is this clear?
yes
Yes,
sir
sir.
Okay. So the point is the properties of this graphene sheet keeps changing. Like you can make different structures out of it and nanostructures, nanoparticles. And the properties keep changing. Sometimes it's flexible, sometimes it's tensile, sometimes so you can have all kinds of physical properties depending on what type of structures you like. And as a plus, the important thing is where are they used? They're used in drug. Number one use is drug delivery. Like in drug delivery, these are hollow structures. Sometimes what happens is that where's the board? One second. Now, sometimes what happens is most of your medicine molecules, there are two ways of consuming medicine, right? You can either consume them orally or you can inject them into your bloodstream. Uh, the problem with uh, now injecting them through your bloodstream, that's kind of dangerous because it leads to a lot of infections, and plus it's not a very pleasant experience. Uh, and and the number one harmful effect is that directly entering something into your bloodstream, that is going to cause infection because any form of bacteria could actually accompany that. So it's not a very safe way of actually consuming medicine. So the problem with oral consumption is that they have to pass through your acid. There's a lot of acid in your bloodstream. not in your bloodstream, in your stomach. There's a lot of acid in your stomach. So if you consume medicine, the medicine is going to get destroyed by the acid. It's going to get digested by the acid. You don't want that to happen. So one way to do that is you consume a lot of medicine, high doses. You take high doses. That leads to other problems as well. You might get many side effects because of those high doses. The best way is you take the tube-like structure, okay, the hollow tube-like structure that you just made, a nanostructure that you made from a graphene nanotube, and all the drug molecules they're going to get attracted by the van der Waals forces, and they would fit inside that structure. And so the drug molecules are going to get protected. They're going to remain protected by the acids in the stomach. Is that clear? Eba, Rida, Bhaswar, is this clear?
Yes.
So, and your nanostructures are so small that they can enter your bloodstream and they can go through your digestive tract, and nothing would happen. So this fullerene, these hollow structures, they can store things. ठीक है, at the microscopic, not the microscopic, but the nanoscale level, right at the atomic molecular level. They can be devices for storage. Uh, and now what's happening is you're trying to make more intelligent storage devices like these nanoparticles. You're trying to make them more advanced and more intelligent. The way you're doing this is that a lot of a lot of your drug molecules, your medicines, they are very harmful. For example, cancer is one. Like if you do chemotherapy, chemotherapy is very harmful because chemotherapy is poison basically. You're consuming poison to kill your cells. But the problem is you have to kill the right type of cells. Uh, the problem with cancer treatments right now is that if you take chemotherapy, if you do chemo, uh, not only would the cancer cells die off, but your good cells are also going to die off. So a lot of people they have very bad effects of chemotherapy, and a lot of deaths occur because of chemotherapy, not because of the cancer, but because of the chemotherapy. And even your kidneys get destroyed, your lungs get destroyed, your organs get destroyed because of chemotherapy because it's so harmful. So instead of attacking the cancer cells, which are multiplying at a very high speed, they start attacking your organs. They start attacking your brain. I mean, every cell that they get their hands on. Which is why it's easier to cure cancer if it's localized. So stage one cancers they're very localized in a very specific area. So you know where to inject the poison. But if the stage increases and the cancer spreads, then it becomes harder to actually kill the wrong type of cells. So these tube-like structures are now being made more intelligent. You're adding things to it, you're altering the structure so that they release drug at the right moment when they encounter a cancer cell. I mean, the cancer cell might have a certain properties. The cancer cell might have a certain groups. So what they're trying to do is that they're trying to make these outer structures, these nanostructures, more intelligent. They've started adding groups to it so that it's reactive, and but it reacts with a certain group that's, let's say, present in a cancer cell. So as soon as this structure meets a cancer cell, there would be a certain group in the cancer cell, and there would be a certain group in the walls of this structure, and they would interact, and that would open up this uh, ball-like or tube-like structure, and the drug molecule from inside is going to get released. Do you get the idea? Aba, is that clear? Rida, Iba, Bazga?
Yes.
ठीक है?
Yes, sir.
Okay, so to sum it up, uh, this is graphite, single sheet. That's graphene. You make you don't actually make precisely ball like. I mean, you can actually make ball like structures and tube like structures from graphene. Graphene on its own, it's very useful because you can. I'll send you a small sheet on this. ठीक है? I think I have some notes on this. You just need to know very general things about this. It's used in photography. It's a very sensitive material. It has delocalized electrons. It's a very good conductor of electricity, and it's very sensitive as well. So it's used in imaging a lot. Many other uses, even for gas storage. Like gas particles, they try to remain as far away from each other as possible. So if you have this hollow cylindrical structure which has van der Waals forces, gas molecules, you can sort of fit them inside, and the particles, how can you put the gas particles together? Because the gas particles try to, let me show it over here, 1 second. I mean, the same thing, gas particles want to remain as far away from each other as possible, right? So you have to exert a very high pressure to bring them close together. But if you have a nanotube and lots of nanotubes, let's say nanotubes stacked on top of one another, these nanotubes have these weak van der Waals forces, and what they're going to do is that if they see a gas molecule, they're going to absorb the gas molecule. So they're very absorbent materials as well, because their hollow cylindrical structures can attract because of the van der Waals forces, and they can store. So you don't have to actually apply a very high pressure. Uh, so that's another very useful purpose of nanotubes. And this is the reason why charcoal is actually uh, charcoal removes impurity from water. I mean, this is what charcoal actually does. It has nanotubes in it. ठीक है? Is that clear as well?
Yes, sir.
Yes,
Yeah.
sir.
चलो ये मैं पता नहीं किधर चला गया. 1 second. अच्छा, so the next thing is, uh, are all electrons localized? That's only diamond. Diamond has all 4 electrons that are completely localized. Next one is, that's a moles question, which is, the board is, don't know what happened to the board. It's moving. So an ore of copper contains 3% copper carbonate by mass. Which mass of copper would be obtained from 1 ton of the ore? So I mean, this is a simple question, that you have copper carbonate, and the ore contains, so it's 1 ton, right? It's 1000 kg, or 10 power 6 grams, right? And first thing is, you're going to multiply it by 3%, because it only contains 3% copper carbonate. So if I do that, I'm going to get the mass of the copper carbonate. The next thing is, what is the mass? I'm going to find the percentage mass of copper in copper carbonate. That would be, copper is, I think, 63.5 divided by the total, which is 63.5, multiplied by 12 plus 16 times 3. So this was the mass of CuCO3, the first one. This was the mass of CuCO3. And this other thing was the percentage of copper in CuCO3. You multiply the two and you get the amount of copper in this ore. Is this clear? You had 10 power 6 grams of the ore, and there was only 3% copper carbonate. So I multiplied that and I got the mass of copper carbonate. And then I figured out that in what's the percentage of copper in copper carbonate? That's 63.5 divided by the total. So I just multiply both of the things, and I'm going to get the mass of copper in the ore. Is this clear to everyone? Abba, is this clear? Hiba, Basga?
Clear.
Yeah, it's clear.
So now next one, the catalyzed formation of ammonia by the Haber process can be represented by the equation shown. Which change in conditions will increase both the rate of formation and the equilibrium yield of ammonia? So you want more ammonia at a faster speed. First one, if you decrease temperature, could you obtain both things?
No, sir.
But what would happen and what would not happen?
Sir, it won't be achieved quicker, but the result, but ammonia would be produced more, but it won't be achieved quicker.
Okay, so there's going to be
Because the
higher yield.
temperature.
Exactly.
Yeah.
because lower temperature favors exothermic reaction, right? So it is an exothermic reaction. You're going to get more ammonia, but the temperature is lower, which means ज़्यादा देर से it's going to take a much longer time. What about increase in temperature? What's going to happen and what's not going to happen?
This will be the opposite of the first one.
Opposite of the yes.
ठीक है, so it's going to be faster, but you're not actually going to get ammonia. You're actually going to get the reverse, right?
Yeah.
I said, what about increase in pressure? Which side would be favored?
This is correct. Yes, exactly. Right side.
ठीक है, less gas moles. That's the right side, less gas moles side. Because there are 2 moles, and over here there are 4 moles.
Three.
Yeah. So the yield would be higher, and whenever you increase pressure, the rate also is higher. So the reaction would be faster. ठीक है? Eba, Rita, is this clear? Abba, is this clear?
Yeah.
That's the next one. What is the standard enthalpy change of atomization of sulfur? I mean, what is the definition first? Can anyone tell me what the definition of atomization is?
1 mole of substance is.
नहीं. 1 mole तो है. 1 mole of what?
Of sulfur, right?
Can you tell me
1
the
mole
exact
of product. 1 mole of product. 1 mole of product. That is
1 mole of gaseous atoms are produced. It's the reaction. It's the enthalpy change of the reaction in which 1 mole of gaseous atoms are produced from what?
from a gaseous substance.
From the element in its standard state.
Achha.
In standard. So that is enthalpy change of atomization. Standard enthalpy change of atomization. That 1 mole of atoms, gaseous atoms, are produced from the element in its standard state. For example, chlorine. 1 mole of gaseous chlorine atoms are produced from its element. What is the element in its standard state? It's Cl2, right? And it's gaseous. So if you want to keep this as 1 mole, this should be half Cl2. Is that clear?
Yes, sir.
Yes.
ठीक है. So what about sulfur? Which one is the correct one for sulfur? Like 1 mole.
B.
I mean, these two are. I mean, this part is correct. ठीक है, and it's going to be
B.
sulfur. Do you have any idea what sulfur is?
Yes, sulfur is solid. Sulfur is solid.
Okay,
Yeah.
the element in its standard state. So sulfur is a solid, right? So it's going to be A. One thing that's probably missing is that you should know that sulfur is S8. Okay, that's part of inorganic. That's the formula of sulfur. It has 8 atoms in it. But even if you hadn't known that, you should have guessed that 1 mole of gaseous sulfur is formed from its element, and the element sulfur is solid. So that's the only option that you have. Next one. Next one is the tough one. It's about balancing redox reactions. They're saying what's the ratio of C to D in the correctly balanced equation. Now, how do you balance a redox reaction? Number of electrons gained and lost must be equal. If something is getting oxidized, something is getting reduced, they should be equal. Now, this is a disproportionation reaction because the only element that is getting oxidized and reduced at the same time, that's Mn. I mean, there's no other element. H is +1, O is -2. It's Mn that is getting reduced. So Mn goes from +4 to +2, which means that it gains 2 electrons, right? And at the same time, Mn is the one that's going from +4 to over here. Mn is +7. Okay? Hopefully you know this already. MnO4 -1. You can either calculate this or you should know this already. So it's going from +4 to +7. That means it lost 3 electrons, right? Abba, is this clear? Rida, Hiba, is this clear?
Yes.
ठीक है, बाज़ clear है?
Yes, sir.
अच्छा, so So next step, what is the next step? Make them equal. Make the number of electrons that are lost and that are gained, they should be equal. So what should I multiply? I should multiply both of them by a certain number. So gains 2 electrons. What should I multiply this by? And lost 3 electrons. What should I multiply this by?
So this by 2 and that by 3.
So I should multiply this by 3. Like there should be 3 MNs doing that, right? And there should be 2 MNs doing this. Then the number of electrons lost and gained should be equal. So D should be 2, and this Mn over here, there should be 3 of them, right? So at the start, there would be 5 Mns because the starting point is the same. So 3 Mns are doing this thing. They're gaining 2 electrons, and 2 of the Mns are losing 3 electrons. So the number of electrons gained and lost are now equal. So there should be 2 Mn plus 7s, and there should be 3 Mn plus 2s. And you can balance the rest of the equation, which is 10 oxygens on this side. So there should be 8 already there. So I think E should be 2. Is it right? Is the oxygen balanced? Okay. Last thing is you balance all the remaining atoms. So let me do that. There would be 2 H2Os. The oxygens are balanced. And there are 4 hydrogens on the right side, so there should be 4 H plus 1s. Okay, Rida, Abba, is this clear? Bazga? And so what's the ratio C to D? I said they were just asking for this. It's going to be D. Okay, it's going to be D3 ratio 2. And also let me check what the number 5, right? 5 is D. Okay, that's fine. Is this clear to everyone?
Yes, sir.
I said next one is in the question you should assume air contains 21% oxygen. So what is the minimum volume of air required to ensure complete combustion of 10 cm? So this is happening under room conditions. So you have to remember this. This is very important. Okay, moles in O levels is different from moles in A levels because in A levels gases can expand and also contract. So under room condition, that means 1 mole of gas would occupy 24 dm cube. So you don't have to. I mean this statement is only true if you're doing this at room conditions. Whenever you're dealing with a question on gases, make sure they're mentioning room conditions or not. Because if they're not talking about room conditions, then this thing would not be true. One of the formulas of moles would not work, which was volume divided by 24 dm cube. That's not going to work. Uh, then you're going to use PV is equal to nRT. As anyways, you have 10 cm cube of butane. What is the minimum volume of air required? So butane is C4, H10. We just did that, and it's going to react with oxygen. And it's going to produce CO2, and it's going to produce H2O, and there would be 4 CO2s, and there would be 5 H2Os and 8 oxygens. Plus kitne 5. 8 plus 5 is 13. So there would be 6.5. Correct me if I'm wrong. 6.5 O2s. So another thing about gases, mole ratio and volume ratio of gases is going to be exactly the same. So if there's 10 cm cube of this, then there would be 65 cm cube of O2. Remember this. I mean, you can get the answer by calculating moles, but there's no need to calculate moles. Remember this, for gases, the mole ratio and volume ratio is always exactly the same. So if there's 10 cm cube of hydrocarbon, like it's 1 ratio 6.5, so 10 would react with 65. If one produces 4 CO2, 10 of them, 10 cm cube would produce 40 cm cube. Okay, so remember, you can answer this question directly. So the answer should be 65 cm cube or not. Is 65 the correct answer or not? Anyone, Ibrar?
Yes, it is.
No.
Abba? It's not actually, because they're not asking for the volume of oxygen, they're asking for the volume of air. So what we need is 65 cm cube of O2. So how much air would be required? like you have 21 cm, so you're going to use ratios. 21 cm cube of O2 is present in how much? In 100 cm cube air. So if you want 65 cm cube of O2, how much air do you need? So it's going to be, you're going to cross multiply and find out what the answer is. Okay, I
You
think it's,
said, how did you do this? 21 for 100 and 65 for X.
but air ka nikalna tha na. He had already told us that 21% of air is oxygen, right? So if I have,
G.
so I'm just using ratio. Okay, if I have 100 cm cube of air,
Mm-hmm.
so how much oxygen do I have in that? 21 cm cube, right?
अच्छा 21% ही.
So हमें कितना चाहिए? हमें 65 cm cube oxygen चाहिए ना? So if I need
जी.
65 cm cube of oxygen, so how much air should I have? ठीक है?
अच्छा जी. थोड़ी समझ नहीं आई मुझे. इसकी मतलब air won't be oxygen, मतलब won't be considering air as oxygen.
We're not going to be considering air as oxygen because he said assume that air contains 21% oxygen.
सर तो हम ऐसा भी कर सकते कि if we get 65 we can calculate 21% of 65.
नहीं, why do you
हाँ अच्छा
65 तो वो है oxygen है, it's not air.
65% oxygen है जी.
बस 65 cm cube तो oxygen है ना. तुम oxygen पे दोबारा percentage क्यों apply कर रहे हो? What you could do is, बस समझ आ रही है ना, बस 65 cm cube के ऊपर you're not going to apply the percentage. वो जो percentage है वो air के ऊपर apply हो रही है कि 21% of air is oxygen. Is that clear?
yes sir.
तो मतलब अगर उसका भी करना है ना तो 21% of मतलब 21 over 100 into x cm cube of air should give you 65 cm cube. You could do this कि ये air है.
अच्छा जी जी अच्छा ठीक है get it.
ठीक है.
जी.
अच्छा, so next one. And remember you just have 1 minute to do this. Okay, you have to be very quick. You have to practice a lot of past papers. The main, it's not difficult to actually solve the question. It's to solve it very quickly when you're running out of time. You don't have a lot of time to solve all these questions. So next one is when aqueous bromine is shaken with cyclohexane and allowed to stand, two layers form. The top cyclohexane layer is colored and the bottom aqueous layer is almost colorless. Aqueous layer. Okay. So what is the most likely explanation for this observation? So he's saying aqueous bromine. Okay, let me second. So they're saying aqueous bromine, right? Now you have water, you have bromine, and you have cyclohexane. Cyclohexane is let's say it's C6H12. Okay. Can anyone tell me which one of these is polar?
Water is polar. Okay.
Okay, water is polar, and it's very strongly polar. Hydrogen bonding करता है water, so it's a very
Okay.
very polar molecule. ठीक है, Rida, Aba, is this clear? Aba, clear है? So this is a very, and what about the other two? Are they polar or non-polar?
Both of them are non-polar.
ठीक है, carbon and hydrogen bonds are non-polar or almost non-polar, and bromine molecule is obviously non-polar because they have the same electronegativity, so the electrons are going to be perfectly shared. So what do you think? Where do you think bromine is going to be more attracted to, or which would it would it dissolve in hexane, cyclohexane, or would it dissolve in water?
Most probably in water.
नहीं, why water? Solubility का rule ये याद रख लो. ठीक है, let me do this over here. Okay, remember this polar जो चीजें होती है ना, But if you have the same type of intermolecular forces, they're more likely to mix. Okay, again, if you try to dissolve water with bromine, right? There's a beer molecule and there's another water molecule, right? Let's say I've mixed them together. Water is polar, and the bromine in the middle is not polar. Well, which of the two would attract each other?
Water molecules would both of them will attract each other.
So the water molecules are going to attract each other, the negative and positive, and the bromine molecule would be pushed aside. Is that clear? So bromine would not be able to mix with water. Is that clear?
So that's yes, sir. But won't it actually get a partial positive and partial negative charge because of the electrons being pushed by the
No,
oxygen atom? That
no,
जी
that would happen. It's going to have temporary dipole induced dipoles, but the force
जी
of
जी
attraction is going to be relatively weak.
अच्छा all right.
Okay. So even then the water molecules would be attracting each other very, very strongly, and bromine is not going to be attracted that strongly. Okay. Is this clear? Baza, is this clear? Abba, clear?
Yes.
Acha, so remember this. Same type of forces, they mix with each other. So what if you didn't have water? So one thing is clear that bromine is not mixing with. I said one thing is clear that bromine is not mixing with water, right? So what if you have cyclohexane? Cyclohexane is nonpolar, C6H12, I think. C6H12. And let's say there's a bromine molecule right in the middle, which has mixed with them. Is there any reason why they should unmix? Like, are any two particles attracting each other very, very strongly? They all have van der Waals forces. So so it's not that these two particles are attracting each other very strongly, that they're going to push the bromine aside. That is not going to happen. Jisa pehle hua tha. In the previous one, you had water molecules attracting each other so strongly that the bromine molecules got pushed aside. But now that's not going to happen. Is that clear? Hiba, Rida, is this clear? Baza, clear? Ibrar?
So clear? Yes, clear.
So okay, the point is polar would dissolve polar and non-polar would dissolve non-polar. But that thing would not happen. That one molecule is polar and the other one is non-polar. They are not going to mix. They're never going to mix, right?
So why isn't the C6H12 and C6H12 not mixing?
Nee, mixing with what? I mean, they are mixing with bromine. Like,
You said both of them, only the two molecules of C6H12.
नहीं फिर तो mixing का कोई concept ही नहीं है ना फिर तो they're the same particles, right? I'm just saying I'm mixing bromine with it, right?
Oh, अच्छा.
So bromine is going to easily mix with them. Why? Because the two molecules are not going to push bromine away. Because the two molecules are not attracting each other that strongly that they would push bromine out of the way. Okay, is that point clear?
जी sir.
So coming back to the question you have, okay, the bromine would probably mix with the. I mean that's my hunch. The bromine would probably mix with the cyclohexane layer, and it would. I mean the water layer would become separate. So that is what he's saying, that the aqueous layer is almost colorless. That means there is no bromine in the aqueous layer. Okay, this is what we decided. And the top cyclohexane layer is colored. Bromine is orange or red brown, so the cyclohexane layer is colored. Abba, is this clear? Do you get this?
Yes, sir.
Achha, so what is the most likely explanation for this? I think it's probably B, but let's. Bromine molecules are non-polar, so non-polar mixed with non-polar. Uh, there's obviously not a reaction happening because it's still the product of the reaction between. Uh, I mean, that's the only explanation. That's good enough. That bromine is non-polar, so it's not going to attract water molecules. It's not going to be attracted by the water molecules. So you'll ask, which in which change are only temporary dipole? Which one has temporary dipole induced dipoles only? First one, what type of
Uh,
intermolecular
yeah.
forces are there?
Temporary dipole, induced dipole, plus they have the permanent dipoles.
No, not permanent dipoles. When you have OH bonds, what intermolecular forces exist?
Hydrogen bond.
Okay, hydrogen bonding when O, N, or F, the most highly electronegative elements, they're bonded to H. It's a very highly polar bond because of the lone pairs on the oxygen and nitrogen and fluorine. The polarity is even higher, so there's very strong attractive forces. So that's hydrogen bonding. Uh, so so this is hydrogen bonding. He's saying only temporary dipole induced dipoles. What about water? What intermolecular force?
What? Yeah, hydrogen bond.
Okay, that's O and H as well. So hydrogen bonding. Van der Waals, remember, is present in every molecule. It's always present. Okay? But now he's saying
Yeah.
only van der Waals forces, only temporary dipole induced dipoles. What about oxygen?
Oxygen has
Is it
it's non-polar. It has no forces. It has
okay? So
yes, it has. Acha, acha. Ji,
so only van der Waals forces, right?
ji,
Because it doesn't have a permanent dipole.
yes.
Uh, and it's non-polar. The only thing is that temporary dipole induced dipoles are going to be produced. So
Mm-hmm.
oxygen, and this is also non-polar. So it's either C or D, one of the two.
Ji.
And he's saying forces are overcome. You're breaking them. So that's
Mm. Would actually change state.
new. So which one? Solidifying or melting or freezing?
Uh,
Where do you?
so,
E.
C, solid to liquid. Yeah.
Okay, so
Ji.
it's going to be C. So okay, let's continue with this tomorrow as well, probably. Okay, then we're going to continue with organic.
Chalo, thank you. Thank you, sir. Allah Hafiz.
Okay, take care. Love is bye bye.